Okay, so welcome back. Welcome to the last talk of the first day of the workshop. It gives me great pleasure to introduce the third of our keynote speakers, Guy Nason, who's Professor of Statistics at Bristol, and he's going to be talking about detection and exploitation of non-stationarities in time series.
Thank you. Is this working? Can you hear me okay at the back? Good, thank you. Okay, so first of all...
Yeah. Can you dim the front lights a bit?
Oh yeah, thank you. One more?
Yeah, one more.
Can you do one more, please?
Yeah. Two more.
Two more.
That's okay. It's good.
Can you do these ones? Can they go? That's it. All right, thank you. Well, here we are. So can I just first of all, like the previous speakers, thank very much the organisers of this particular workshop and the very exciting looking programme that we have here in Cambridge. Also thanks to the Isaac Newton Institute, because of course all the hard work that they do means that we can sit here and just talk about statistics and mathematics and related subjects all week and not worry about other things. Looks a great programme. Really looking forward to watching all of the talks. This talk here is what is down as a keynote talk. I'm not sure what a keynote talk is, so I asked the organisers what's a keynote talk, and I'm not sure they gave me a really good answer. No, they did. So it has some aspects of an overview. So some of the work I'm going to be talking about is most definitely not mine, but belongs to some people in the audience actually in some cases, and others if not. But as David said, some of the talk is necessarily coloured by my own history and background and some of the work that I've done to try and really illustrate some of the concepts and theories rather than anything else. And in fact, the newer work that I'm going to be talking about here near the end of the talk is with some co-workers, Alessandro Cardinali, who's now in Plymouth, Idris Eckley, who you met first thing, Rebecca Killick, who's at Lancaster, and Marina Knight, who's at York. And before I go any further, I wanted to just also mention Rainer von Sachs, because he was the guy that really got me into this area of time series analysis. I'd already done some work with Bernard Silverman on how wavelets, those things for estimating curves, could be used for a kind of rudimentary spectral analysis, and I think I remember Rainer coming up to me and saying, no, you're doing it all wrong and we need to do this, and this. Well, it was something like this. Anyway, so let's get going. So I'm going to be talking about, when I work out how to use this, oh, there we go. I'm going to be talking about non-stationary time series mostly. A key theme that's going to run through the whole talk is this idea of multitude of representations, because I personally think this is an important area for the future, and it's something I'm very excited about, and it also interestingly links back 50, 60 years in quite a nice way, as I'll show a little bit later on in the talk. A key item I'm going to be talking about are tests of stationarity. And the more I learn about tests of stationarity, the more tests of stationarity I find. So it's a very interesting area. It's also a very hot area, I think, at the moment. Picking up on something that Rainer Dahlhaus said earlier on, I'm going to be talking about localized autocovariance and trying to develop that a little bit more down in that area there, and say a few words about forecasting, because I think this is something, strangely enough, there are a lot of statisticians that do this, but it's kind of maybe a slightly forgotten area, possibly, I don't know. This is a very Mickey Mouse slide. What's time series about? Well, you know, we want to model them, we want to estimate parameters, check model fit, try out the models, forecast future values. We need models. So really a lot underlying my talk is going to be models. I'm not going to be talking about changing the data, i.e. someone comes to you with a time series, gives it to you and says, analyze it, come and give me some interesting stuff. Well, you know, you could go back and say, well, actually, I don't want that data, I want this data, I want it sampled at a different rate. Again, we don't do enough of that, I think, as statisticians, although some of us, of course, will do. I need to acknowledge a particular data source in my talk, otherwise, especially since it's being live streamed, I'll get sued immediately if I don't mention it. So some of the data comes from the UK Met Office, and it's distributed through the NERC British Atmospheric Data Centre. And acknowledgement and thanks is obviously due because they spent all this time, effort and money just to give me data to analyse, so thanks to them. Here's that particular data set I'm going to be looking at occasionally. It's one of my favourites, or at least one of my from a favourite class, which is energy time series, and this is a wind speed, an hourly wind speed, and it's a record taken in January 2009 in Cornwall. And it's hourly data, and there is about 3 weeks of data there, and you can see some kind of trend there. It's measured in knots, which is why they don't use meters per second. I don't really know, but anyway. But there's a kind of trend going on there, so a typical statistician might well difference that. There are other things you can obviously do to get rid of the trend, but I'm going to difference it. And what really strikes you is this kind of big pulse here, and that corresponds to, I guess, 3 or 4 days, which is roughly when some kind of pressure system is passing over Cardinum, and you've got like a volatile weather system, and then you'll have slightly quieter periods and more volatile periods. Okay? In the wind speed arena, you have many people modeling wind speeds and trying to especially forecast them and provide short-term forecasts so that the power that feeds our grid, they can correctly accumulate all this power from different sources. So forecasting is important for balancing the grid, it's forecasting for selling the power on the grid. And most of the methods that I've seen them use, although it's not all of it by all means, but are stationary type methods. Okay, and this may well not be a stationary type series, and this might be a period where the variance changes suddenly or something else. So obviously we're interested in questions of whether a time series is second order stationary. Just to show you where Cardinum is, it's just down there. In the middle of one of the moors, Bodmin Moor in Cornwall, and I have many other data from the same set, from the same time, and obviously the question of multivariate time series is something that's very important and actually very pertinent for forecasting of wind speeds. Before we go back to data, I'd like to remind you of this gentleman, and I'm going to use a lot of material from Maurice Priestley's book. One of the reasons was I was fortunate enough to speak at Maurice's special day. Maurice Priestley died last year, and there was a day in celebration of his life in Manchester towards the end of last year. And I had the privilege of really going back through Maurice's book and picking out lots of really important things, a lot of great material in there. And so there'll be a thread running through this, kind of picking up on what he said, and almost how he foresaw quite an area of, I guess, applied mathematics in terms of applied computational harmonic analysis from some of the things he was doing turning up in this ACHA domain today. Maybe in a different way, but basically those kinds of ideas. So this was one of the things he wrote, was that the classical methods of time series analysis are based on 2 crucial assumptions, namely that all series are stationary, at least to order 2, and all models are linear. Okay, so that's maybe the baseline of where we come from. However, stationarity and linearity are approximations to the real situation. Now, I suspect almost everyone in this audience knows that. I'm not so sure about everyone outside knows that or appreciates that or even thinks about that. Okay, so I think one of the outputs of this meeting is maybe to publicize that whole thing to a wider audience. So what did he do? Well, he was interested in establishing a method of characterizing non-stationary processes, and he described non-stationary processes based on his theory of evolutionary spectra in a number of papers. And how did he do that? Well, he introduced this concept of an oscillatory function, phi t of omega, where phi t of omega is equal to a t of omega times by e to the I theta of omega of t. So a of t of omega is a kind of amplitude function, has this representation, this kind of Fourier representation, with dk omega of u having an absolute maximum at frequency u is equal to 0. So basically, there's some DC power, there's some kind of smoothie, constant kind of stuff at 0 frequency. That's the amplitude function there, times by this oscillatory complex exponential. And then with that oscillatory function, he forms what he calls his oscillatory process. So the stochastic process x of t, which involves essentially a summation of the oscillatory function with some orthogonal process, which he calls z of omega, with measure mu there. And then he goes on to define some of the things we're familiar with very much these days: the evolutionary power spectrum at time t, dht of omega, which is equal to the amplitude squared in modulus, times by this d mu of omega. So for example, when x of t is stationary and phi omega is equal to omega, then dht of omega reduces to the regular spectrum, of course. Ht of omega is the integrated time frequency spectrum. Oops, sorry. Assuming enough smoothness in the right places, the evolutionary spectral density function is ht of omega. Okay, so that's the kind of time frequency spectrum that a lot of us play with in various different settings these days. Now, rather than go through the whole theory of estimation with this, you can go and read it in the book yourself. Although it's good obviously to quote a lot from Morris's book. I can't spend a whole talk just reproducing the book. You'd sack me immediately. But I wanted to focus on a few aspects of that. So Priestley in '65 came up with a very nice double window method of estimating the time frequency spectrum, ht of omega, with the hat for estimate. But one of the key things that came out of his body of work was of course the stationarity test published with Subaru in 1969, and others that obviously did things before that, but this was a particularly, I guess, landmark paper. And how does he do it? Well, he defines yt of omega to be equal to the log spectrum, and then approximately the expectation of that y is equal to the log of the truth that you don't know. But crucially, the variance is approximately stabilized by taking that log transform. And then he had the great idea of writing that y in terms of this log spectrum plus some noise process epsilon, which he then discretized over a set of times, t1 up to ti, and frequencies w1 up to wj, to get this nice linear model representation where the yij, which would have been the log spectral estimate, you model that as a mu plus alpha I plus beta j plus an interaction term plus the epsilon ij. And actually, if you space out the times and the frequencies enough, then you get an approximate IID exponential Gaussian distribution of the error. Okay, what are we interested in for a test of stationarity is the spectrum constant over time. Okay, and where does that turn up? That turns up in the alpha I. Okay, so over times I, and also in the interaction term as well. And so the test of stationarity is, are all of the alpha i's equal to 0, and are all the interaction terms equal to 0? And that's the test. Okay, so I'm an applied statistician. I want a test of second order stationarity. I can go and read Priestley's paper or many of the others that have come, but I don't want to read all that stuff. I want a test. I want a piece of code to go and do it. Well, fortunately, there's a package called Fractal in R. There's a function called stationarity. It uses an improved estimate of the spectrum and a multi-taper estimate, which reduces the bias. And this was posted in 2007 by Bill Constantine and Don Percival at the University of Washington. And that was on CRAN for a while. Unfortunately, it's now off CRAN, and it's in the archive. So if you know what you're doing, you can take it from the archive, you can fix it up and make it work. But, this is, come on guys. I'm not blaming them. It's R basically changes every 5 minutes, and you have to then adapt to keep your package up to date to try and keep up with R. Okay, so it's a bit tricky. But it does exist, and you can use it. But amazingly, 38 years after the original paper. Yeah, for something as simple as testing for second-order stationarity. Yeah. So one good thing is you can say those guys were way ahead of their time, maybe. Okay. And if you're interested, for the cardinum data, the software comes back and gives you a ridiculously small value for whether it's stationary or not. So there's very strong evidence, as you expect from looking at that picture, that it's a stationary, a non-stationary time series. Now I want to move a little bit in a different, slightly different direction. And I was looking at something in Priestley's book, which I'll mention on the next slide, which referred to a technical report by Manny Parson from 1959. And amazingly, Stanford have all these on their website. It's just a real pleasure to see all those there. Okay, but why did I put that on? Well, in Priestley's book, he mentions Parson and says that he pointed out that if there exists a representation like we just saw, so this stochastic process with the oscillatory function and the orthogonal Z, then there exists a multitude of different representations of the process, each representation based on a different family of functions. Okay, well, that's an interesting thing. The situation is in some ways similar to the selection of a basis for a vector space. Okay. However, if the process is non-stationary, this choice, and by that he means the usual regular complex exponential family with the constant amplitude, by the way, this family of functions is no longer valid. Okay? So let's go back to Priestley's oscillatory functions again. He actually settles on, in the end, theta of omega is equal to omega. So the oscillatory function becomes this time-varying amplitude with e to the I omega t. That's nice. It captures the class of uniformly modulated processes where at of omega is equal to c of t. Okay, so the modulation is the same at each frequency. And then he goes on to develop a class, what he calls the semi-stationary processes. And essentially this comes from the idea in stationary time series theory where you have a regular frequency response function gamma of omega. And he picks up on the useful property that if you take a time series x, you run it through a filter. So you take a stationary time series x, you run it through a filter, gamma, the output is hy. Then the output spectrum at omega 1 is only influenced by anything at frequencies at omega 1 on the input. Yeah, if and only if. And he mimics this stationary case for the non-stationary situation and uses that useful property. And how he does that is he achieves it by letting the at of omega evolve slowly as a function of t, and he gets his semi-stationary processes. And I only mention that really is because, yes, obviously that's exactly what he does, but people these days tend to talk about time-varying evolution of spectra should be slow, so you get a chance of estimating the patches of stationarity, if you like, as you're going on. So it's kind of the same thing, but justified, I guess, from a different direction. The other thing we have to think about for non-stationary processes is the Heisenberg-Gabor uncertainty principle, which says, and again this is from Priestley, the more accurately we estimate ht of omega as a function of time, the less accurately we can estimate it, we can determine it as a function of frequency. Okay? So, again, well known for a number of years, comes from quantum mechanics, I guess, originally. But to estimate the time-varying behavior, we will necessarily have to sacrifice some frequency resolution. We can't have everything. And this is also an advert for Jean-Marc Freyemuth's talk, who's later on in the week. So he, I guess, touches on some of these and takes them in that direction. So, if we have to search for other bases, what do we do? Okay, where do we go? We've got the Fourier, of course. We know how that works. For a time-varying Fourier, we get t time steps, t over 2 frequencies, something like that. Wavelets, Rainer kindly mentioned our paper earlier. There are wavelet non-stationary process representations. There you will have t time steps, but log t frequency bands. There's a different splitting up of the time frequency plane. But these are just single bases. Why should we pick these two preferentially out of all the many bases that we might want to use? Well, there could be very good reasons for that. Obviously, if you're in a situation where you're modeling a locally stationary series which is pretty close to stationary, then clearly the Fourier is going to be a good idea, or divergences from Fourier. Okay. There are articles on Walsh series representations for time series, many others. However, for some of the things I want to do, I want to move not to using a single basis. I don't want to have this problem necessarily of choosing this basis or that basis for some of the things I want to do. What I might want to do is just throw a whole library or a whole dictionary of bases at a particular problem and see whether that gets me further along the line. So what do I mean by that? Well, I'm going to show you some in a second. Here's a few buzzwords: local cosine or sine bases, wavelet packet libraries, and a lot of this comes out of the work of Koifman and his work of adaptive waveform analysis, and there are many other people as well, but that's a good central name to look for. And let me tell you about local cosine bases quickly, because it relates quite strongly to what Priestley was talking about many years ago. So here's a Bell function. I don't want you really to get hung up about what the exact mathematical function is. It looks a bit like the bottom of a bell. That's why it's called a Bell function. But it's like, I guess, some kind of window function, and we call it b of x. And here's the definition of a local cosine basis, which I actually took out of Walter and Shen's book, but it's originally due to Koifman and Meyer. I don't want you to read and internalize that whole definition. You can if you like, but please don't feel forced to. What I want to focus on is this line: let b k of x be the epsilon k plus 1 bell. So we're moving the bell around according to k. And this line, where I take cos of x with some other parameters to shift it around a bit, but basically cos of x times by the bell. Okay, so that's what it is, cos of x times by the bell. But now I want you to remember what Priestley was talking about, where he had at of omega times by the oscillation. Okay, so this is maybe a more developed, a richer set of bases, but essentially the core of what was going on here is very similar to what Priestley was trying to get at. So here's some pictures. Here are 3 local cosine basis functions using the bell that we just saw. So you can see they're a bit sinusoidal. They wiggle. They're a bit like wavelets because they're local wiggles, but there's not a symmetry like you would with sines or cosines. And of course you can get many others. Here's 2 other local cosine bases, and there's whole papers of has whole bodies of work on the organization of these things, how you compute them, how you can pick some out, threshold them, all kinds of stuff. But let's go back to Priestley and the multitude of representations. So as he said, there's a multitude, each representation based on a different family of functions. So there are many things. Now we have these wavelet packets or local cosines. There are many things that we might try. The world is maybe richer in terms of these applied computational harmonic analysis tools. Not all of them will turn out to be oscillatory functions in the lingo of Maurice Priestley, or they may be, or we don't know, or we don't necessarily care. One particular example, as Rainer mentioned earlier, are wavelets, and there's a pretty well developed theory for those in the locally stationary wavelet processes. And if you haven't seen this before, then x of t is the stochastic process. The psi j k minus t, well, they are wavelet basis functions. They're actually discrete wavelets, so vectors of oscillations, if you like, and at scale j, so you have large scale oscillations and small scale oscillations, and you can move them about the axis by changing the second argument there. We've got k minus t, which gives you a convolution. There's randomness, psi jk, that's just a collection of IID random variables, and amplitudes there, w jk. So this is very similar to the Cramer representation, and instead of Fourier functions you now have wavelets. Instead of the orthogonal process you have the psi, and instead of the amplitude a you've got amplitude w. And if you add all those up you get a model for a time series. A particular model, and quite a few differences from the Fourier model, but this is the idea, to show you that there are different representations and somehow quantify them a bit. So let's go back to the idea about testing for stationarity. And I recently wrote a paper what I want to use for an example. In that, because it's going to show you a class of examples. So how does this test of stationarity work, and why is it different to the Priestley version? Well, first of all, we compute something which we called, in this 2000 paper, the raw wavelet periodogram, which is equal to djk squared. What's djk? It's just the discrete non-decimated transform of the data x. So this is completely analogous to the usual stationary spectrum, where you would take a time series x of t, you would take its discrete Fourier transform, you would then look at the squared modulus of the coefficients, and that would give you the periodogram. This is the equivalent, this is the wavelet version of that. I just say. And I'm also going to define this beta j of z, which is the expectation of ijk. Okay. And the null hypothesis turns out to be that your process will be stationary if this function beta j of z is constant. So here there's something happening here, because we've got here in mind a particular locally stationary wavelet alternative hypothesis. But actually I wouldn't need necessarily to put that line up. Okay, so I could put, instead of putting wavelets there, I could put a more complicated oscillatory function in there, still do more or less the same stuff, and come up with a test, and not necessarily think of anything in particular as a model for an alternative hypothesis, which kind of gets you into the engineering testing for stationarity.
Yes and no. I mean, I think one ingredient of our model was that this is rigorous. Under H null, this function is really constant over time, which is not necessary if you just take arbitrary oscillatory or whatever functions.
Yeah. Sorry, that's what I was trying to say, but maybe didn't say it very well. Yeah. Okay. How constant is your function?
I think your mic is not working anymore.
How is it now? Is it working? Oh no, hang on. There's a little red light.
Now it's going.
That's okay. Yeah, but when I pressed it before, it was a green light. Now it's a red light. Batteries. So nobody's heard anything for the last 20 minutes. Is that working?
Yeah.
Is it? Put it up higher. Is that better?
Yeah, it's good.
Okay, so we still have the problem for the Fourier, or for the wavelet version of this test. We want to see whether this function beta j of z is a constant function or not. And in fact, what I use for my test is the extremely nice paper by Neumann and von Sachs, which checks constancy of these kinds of functions using Haar wavelets. So Rainer, of course, if I get this wrong, you must tell me again. But how do they do it? Well, they work with the locally stationary Fourier spectrum fz of omega, and their aim is to estimate these wavelet coefficients, where these psi jk as functions of time, they're the Haar wavelets in time, and the phi jk of omega, they're the Haar father wavelets, or another smoothing wavelet. They estimate f of z of omega using the pre-periodogram that Rainer talked about earlier on, and here's the formula for the pre-periodogram that you saw earlier. So it's a nice estimator of the Fourier spectrum. And the point is, because you're basically taking the Haar wavelet transform of the spectral quantity in time, if you get non-zero Haar wavelet coefficients, that's an indicator that there's some non-stationarity in the spectrum at that time and at that scale. All right, that's one of the useful things about this test. It doesn't just tell you that it's here. It's kind of gives you some qualitative information about what the non-stationarity is. The wavelet coefficients estimate is this, which is a bit complex, but effectively you can see that you've got their different time-integrated periodograms and then integrated over omega. So it's basically the empirical version of what you saw on the previous slide. So in a sense, it corresponds to a particular decomposition of the time frequency plane because of the underlying wavelet basis functions. The nice parts about their work is they show asymptotic normality for most of these wavelet coefficients. That means you can get a nice test out of that, and here's the theorem that they state. And then you also have to estimate the sample variance sigma. Oops. And the other nice feature of their work is that this is made to work for not just Gaussian time series, but a whole range of other distributions satisfying certain mixing assumptions. So it's almost a very general test. The asymptotic normality, they get that by essentially using the wavelet coefficients that cover enough of the data. But what you get out of this is a multiple hypothesis test problem. So essentially you're looking at your spectral quantity, you're looking at the Haar wavelet coefficients of that over time, and so you have many, many, many Haar wavelet coefficients, and if you've got the right ones, they have an asymptotic normality, and you're testing each one, is it 0 against the alternative that it's not 0. So it turns into a multiple hypothesis test problem. They assume bounded variation, so it can cope with jumpy processes, and as I said, it can locate the non-stationarities as well as give you some idea of the scale of them as well, or the frequency. Doesn't make use of fine scale coefficients, I believe. Okay, so that's what we're using for this wavelet test. If you do the wavelet spectrum, you still have to check the theory for that, which is what a lot of the paper's about. We use the Haar wavelet coefficients for the wavelet periodogram, not the Fourier periodogram. But it's still, you have an asymptotic Gaussian theory for these wavelet coefficients, and again, you have to use multiple test control, Bonferroni or FDR or something else. And you can get this stuff that I'm talking about in a package off R called Lossitz. Okay, so if we apply the wavelet-based test to the cardinum first differences, then you can just about see the original first difference time series there. Can you see that okay? All right, good. And then in this particular test, the test comes back and says 7 of the Haar wavelet coefficients of the wavelet periodogram were assessed to be non-zero. Okay, and that's where they are in the time series. So horizontal location tells you where they are. The length of the arrow tells you the support of the wavelet coefficient that was deemed to be non-stationary. Okay, the other number here on the right-hand axis tells you the scale of the wavelet periodogram that where you found the non-stationarity. So here, when you do a wavelet periodogram, you have different scales, and then you do a Haar wavelet transform of that. So these are scales within scales, but it gives you an idea of where the non-stationarities are. And it's a great thing in that the world of stationarity testing, I think, has just kind of exploded or starting to explode. So there's always been a lot of papers, and I think there's just like a huge number of papers really taking off. So I recommend you read all of those. This one I particularly like, by Dwivedi and Subbarao, where they look at the correlation between Fourier periodogram ordinates, and if you have stationarity, you have this asymptotic uncorrelatedness between the periodogram ordinates, and they build a test of stationarity out of that. I really like that because it's a slightly different way of looking at the world. And of course, there are many more. I've not even gone into the world of spatial. Branching out, well, we talked a lot about time series and spectra. There's many other things that we can look at and play with. Localized order covariance and order correlations been mentioned. Forecasting's been mentioned. There's a whole world of multivariate time series. I mean, the data I showed earlier, I mean, that's really a multivariate problem. And again, it's an excellent sign that many papers starting to come up in this general area of looking at multivariate problems. I'm also interested in the areas of network time series, point process time series, ordinal, functional, the question of sample rate, and just to make the general point, there's a lot of interesting stuff to do and plenty for everyone. If I get time, I'm going to mention about network time series as a kind of advert for another talk later on in the week. Well, what I'm going to do for the remainder of the talk is just pick on a few subjects there and just show you some more recent stuff to do with those areas. So localized autocovariance, again, everyone kind of knows, I think, what it is. It's a very simple concept. You take the regular covariance that you love and you know from using ACF in R, for example, and you want something that can give you a time varying localized autocovariance if you have a non-stationary process. Okay. So how could we do this? Well, there are the usual representations, the local stationary Fourier spectrum. If you invert it using the Fourier inverse, then you can get a time localized autocovariance. So here tau is lag, z is time. If you had a locally stationary wavelet process, there's a kind of equivalent formula there which takes the wavelet spectrum, uses a kind of inverse wavelet transform to get you the localized autocovariance. And again, there must be other versions of this whole kind of thing for other systems. But I wanted to show you an example, and here's a picture of a time series called ABML. And ABML is the name of a data set which you can get off the Office for National Statistics website, if you can find your way around it. And what is ABML? It's actually a time series called GVA, which is a component of the GDP measure for the United Kingdom. So it's quarterly data, and as you expect from these kind of time series, it does this kind of thing, which you might see with integrated time series. It's hard to see what's going on with that kind of series, and my first instinct is to difference that, and other people may disagree, but there's been a nice paper recently by Hirokara and Sedakata on doing exactly that. So essentially differencing these kinds of processes and then modeling what you get left by a locally stationary process of some kind. But the general idea is what you would do with ARIMA processes or something like that. So let's look at actually second differences. And here you have second differences of ABML. And it's kind of quite interesting. And what you notice, the very, very strong thing that you notice is that the variation of the time series increases quite markedly over time. But we have, because of the difference, and we've got the zero mean. So this could be right for modeling using a locally stationary Fourier series or a locally stationary wavelet series or something like that. Now, of course, if I gave this talk in front of a set of economists, and there may even be one in the audience, they all say, well, you're mad. You should never analyze this time series. It's the wrong thing to look at. You need to correct for inflation. Okay, so, well, all right, you can correct for inflation, and there are ways of doing that. And of course, you lose that kind of increasing large variance because that's really due to inflation. That's where it comes from. Now, I'm not going to show it, but actually that turns out to be not second order stationary either. Although it is in some sense more stationary than the one I showed you because it doesn't have that big variance increase. However, which one should you analyze? That one, that one, or that one? Because this one is actually the product of two time series which are both subject to all kinds of different errors in the process, and if you really dig into it, they're revising these time series all the time, changing the basis. You know, it's a real mess. So do you really want to deal with the ratio of two very messy time series, or do you want to deal with one very messy time series? Interesting question. I don't know. But the economists will want to look at this. Okay, so we could run the ABML second difference stationarity test again. And interestingly, you have this one big wavelet coefficient here, which is saying I think this whole time series is basically non-stationary, which is what you'd expect with that very large variation increase. But it also picks up some others here, here, and here, which is quite recent in time. But the thing I wanted to get to was looking at autocovariance over time. How does that change over time? Well, you can run that through one of these local autocovariance pictures. And this here is tracking the local variance, and as we know, that increases very quickly over time. That's tracking that. But also, interestingly, the first order autocovariance is changing over time as well. Okay. And sometimes when you look at this normalized, so that you normalize the local variance to be 1 to get a correlation, then you don't notice this changing. But then there are other series where it genuinely changes for covariance and for correlation at the same time. The other thing you can do with a series like this is essentially pick a particular time point. So let's just look, what time do we pick? Q3 1971. So that's somewhere in here. So pick a time point and then tell me what the autocovariance looks like around that time point and give me confidence intervals for those localized autocovariances. So what it's basically saying at Q3 1971, there's nothing significant and the variance is about there because 0 is contained in all of these confidence intervals. What about another time point, Q1 1989? Well, where is that? 1989 Q1, that's there. So this lag 1 autocovariance is bigger now. Is it significant? Yes, it is by now because it's lying outside of the confidence band. So these are approximate confidence bands for that, which are different from the regular ACF confidence bands. Okay, and then you can do it for a later time point still. Okay, so why do I kind of talk about that? Well, kind of theoretically, maybe it's not a very, very interesting thing to look at. I mean, it's kind of almost like a byproduct that comes out some of the spectral estimation stuff. But if you talk to economists or you talk to many statisticians, that's what they're really interested in. They really, really want to know about localized autocovariance. Okay, so methods for doing that better, because remember, this is a wavelet-derived quantity. Yeah, well, the underlying model is meant to be a locally stationary wavelet type model, and your time series may actually be very far from that. It may be more closer to a LSF process, or indeed another one of the multitude of representations. So this particular method might be giving you not particularly good results, and you don't know that. So this is why you need the multitude of representations to kind of ensure against that. So although it looks like I'm telling you the right answer, you should be really questioning this. Forecasting, well, we can't go wrong with forecasting. Obviously a great deal of interest in forecasting, especially in things like economics, the wind energy, for example. And why is this a good time now to get very excited by forecasting? Well, this is a quote from the Stockton Review. So after the financial crash, various important bodies in the UK said, oops, that wasn't a very clever thing. What went wrong? And there were 3 reviews that were launched, and one of them was, how well can the Monetary Policy Committee, which is the committee in the Bank of England which tries to decide interest rates, amongst other things, how well do we forecast? How does that committee get its information? What do the forecasters do? Well, they do a lot of stuff, and they do a lot of fantastic stuff, but this was a very telling quote, which was saying that the large-scale macroeconomic models are woefully ill-equipped to deal with the implications of this type of shock. And basically saying they need to look at different methods of doing forecasting in the future. And I'm going to talk about one particular way of forecasting stemming from locally stationary processes. But there are, again, as Rainer said earlier, there are many, many other smart ideas out there, and as many as possible should be looked at and tested. Anyhow, what is the existing benchmark? Well, it's often in this area ARIMA and variance or slight variations of ARIMA. Okay, so that's the kind of thing that needs to be beaten most of the time. And one of the amazing things, and it just shows how completely ignorant I was, I knew about some of the more recent papers in locally stationary forecasting. I didn't believe that anyone knew or did anything before I was born or something, but actually you just go back through the papers and it's just like amazing, the papers that come up. So I'm just going to pick out a few that I found. A really excellent paper by Peter Whittle on a recursive method for working out predictors of non-stationary processes. A landmark paper again involving Priestley in '67 on prediction of non-stationary processes, developing what we were talking about earlier on. A very nice paper in 1986 by Hallin, looking at time-varying moving average models. a paper by Reiner that also touches on this in a SPA paper in '96. And basically some of these works were to do with time, extending the Kolmogorov kind of Wiener ideas to like a time varying solution of your Walker equations. And then more recently a paper by Piotr, Sebastian and Reiner, and forecasting with these kinds of methods using wavelet processes, and starting to really build a real practical, not just publishing the paper, but writing software and saying what the algorithms were so that people could genuinely pick this up and use them. And more recently, there's been a paper, again, further improving the 2003 paper. So I'm going to pick on this paper from 2003 because it's the one I guess I know the best. And the general idea is quite simple. So with the regular forecasting that you might do with Box-Jenkins, what does that do? It says, well, we want to forecast using recent values of the time series, and we're going to go back and we're going to choose those values and form a linear combination and try and work out what are the coefficients to give us the optimal mean square prediction error. And this does something similar. So you have a linear combination of past values of the stochastic process, where you go back, say, p steps in time. But here, the weights that you're using evolve in time, which is obviously sensible. If your process is evolving through time, if your time series, the stochastic properties are evolving through time, then of course your coefficient sequence should try and track that. That's the whole idea here. And that can be found by, as I say, solving these generalized time-varying Ewell-Walker equations, which is not a trivial thing to do, and it's not either in terms of theory or actually trying to solve them in practice either. And they propose a nice algorithmic method for choosing the key parameters, which include there's a smoothing kernel in there as well, I believe, but particularly the one I'm interested in is how far back do you go in the time series. And in fact, the paper by Z noticed that, well, they kind of mentioned some improvements by regularizing the weights. So recently I've been working on this with Rebecca Killick, Marina Knight and Idris Eckley, and essentially the two things we've been looking at are doing a different kind of smoothing, so using spectral smoothing rather than the covariance smoothing. I think it's more of an alternative rather than maybe an improvement. And the other thing we've been focusing on is trying to choose that P more carefully, or at least thinking of a different method of choosing the P. And the way in which we're working now is to use a local partial autocovariance to choose P. Now, people know about partial autocovariance. It's obviously a very well established quantity, and there's been a lot of work on localized covariance and localized autocorrelation. So it makes sense to come up with the localized partial autocovariance. And you can get some very nice estimators where you can track more AR-like parameters as you would for stationary, but in the non-stationary world. So we're going to try this out, which is always a dangerous thing to do, on the ABML second difference series and ask some questions. So does the actual value lie in our prediction band? And what we're going to do, we're going to be doing 10 one-step ahead predictions. So predict the last observation from the previous ones, and predict the second to last from the previous one, third to last, fourth to last, etc. The truth, remember, is going to be a green diamond. That's the truth. We're going to do stationary Box-Jenkins, the usual stuff. That's going to be in black. The point forecast is going to be a black circle. The confidence bands are going to be little crosses. And using the new updated version of the locally stationary forecasting, it's going to be the same thing but in red. Here's the picture. Now it's a bit complex, but I want you to focus here. This is the end of the series. This is telling us what happens when we try and forecast the last observation in the series. And this is the truth here, the green diamond. This was the Box-Jenkins forecast. This is ours. These are the confidence intervals for Box-Jenkins and ours, the lower one and then the upper one. Okay, so we don't do very well here, but if you go to here, for example, there's the truth. The truth lies outside of the Box-Jenkins, but it lies within ours. Okay, and I won't bore you by going through the whole thing. You can pick it up later. What's maybe more interesting are the summary statistics for this one toy example. So 3 out of 10 of the stationary prediction intervals contain the truth, 7 out of 10 for the locally stationary. You can get some numbers for the mean square prediction error. Ours is a bit better here. The locally stationary forecast reflects the higher uncertainty for the non-stationary series. So you get larger confidence bands here because it's not constrained by this stationarity. And even if you had a stationary series, you'd get slightly larger bands because, of course, it doesn't assume the stationarity. So the method is not overconfident. And one of the problems that the economists have been talking about is that somehow their forecasts always end up being too confident. But what about inflation, I hear you ask if you're an economist? Well, there's the inflation-corrected series. You can do a similar plot. I'm not going to go through it again. Here, because the whole series was a bit more stationary to begin with, then the stationary method does better, but still the locally stationary beats it, and you get, again, better figures for the kind of the time average thing. I think I've said these things already. So, multitude. How long do I have? How many more minutes, say? 4 minutes? Yeah, okay. 4 or 5 minutes, okay. Just finally, let's just talk about multitude again. And going back to this concept of having many different basis functions for analysis of time series, you can start asking questions like, well, if I have a locally stationary wavelet process and I analyze it using a Fourier type method, what answer do I get, and vice versa? And then, of course, you can expand that to all kinds of different basis functions. So here's a theoretical toy example. So suppose you start off with a locally stationary x of t, and I'm going to subject it to, I've picked on this one by von Sachsen-Schneider, this particular local periodogram, but it doesn't have to be that. It could be another one, for example. I'm going to assume no tapering just to make the mathematics a little bit easier. So this is LSW, and I'm analyzing it using, so it's a wavelet process, I'm going to analyze it using a Fourier method. And if I just look at the middle component, and I'm running out of time, so if I do some math, and I assume t is big enough, what I can actually get is that the time-varying periodogram analysis of the LSW actually turns out to be independent of time. Okay, if I choose the right type of LSW process. So if I choose an LSW process where all the action is at the high frequencies in the finest band, and then I do a Fourier analysis of the frequency, it doesn't really pick up the time variation. Okay? So the time varying spectral information cannot be easily detected by the local periodogram. And in a way that makes sense because the finest scale LSW is very broadband. It has a very wide range of frequencies. Whereas the Fourier analysis is, as you know, very, very narrow band. So it doesn't work. And you can do a similar example for an LSW analysis of LSF. So my view is we shouldn't just be thinking, you know, can we do a Fourier analysis or a wavelet analysis? We should be using a richer set of functions. And for example, you could use wavelet packets. There were some pictures there. Here's an example of Haar wavelet packets. So here are the Haar wavelet packets at the finest scale. So this is the usual regular finest scale Haar wavelet, 1, minus 1. And this is the father wavelet, 1, 1, the constant. At scale 2, there would be 2 normal Haar wavelets, which would be this one, which is just the father wavelet, and this one, which is just the mother wavelet. But there are 2 other packets. And obviously at scale 3, there are 8, scale 4, there are 16, and so on. And you can select a basis if you like from those, and some problems do. And now what I'm talking about is not a wavelet test of stationarity, but a wavelet packet test of stationarity. So this slide is the same as the one I showed earlier, except I've replaced wavelets by wavelet packets. So I can do a test for each packet if I like, or I can combine packets if I want. Again, running out of time. The main message is that different packets will look at different alternatives. So you have a kind of directional power here. So this wavelet packet looks for non-stationarities in this direction, wavelets in that, for example. There's a picture of the squared gains to try and show you the frequency spaces divided up. And here's an example. So here's another example of a time series. You can just... sorry, the computer's trying to catch up here. Right, hopefully it'll stay there long enough for me to tell you what it is. So there's a time series, which is the baby data that was analysed in Nathan von Sachs Croissant 2000, the first differences. This is what the wavelet test comes up with, says you have the non-stationarities here. And then what you can do are wavelet packet tests, which is essentially looking at different directions and picking up the non-stationarities in those directions. And you can do an empirical power comparison, and these are the tests from the paper by Holger and co-authors in 2011. These are the powers they've got. This was the wavelet test, which doesn't do very well most of the time in comparison with Holger's paper. But if you use the packet version, it really does find these non-stationarities extremely well. And I haven't shown it in this table, but the empirical size is still well controlled as well. Okay, and that's it. That's all I want to say. I'll just skip over these slides. There's a great talk by Matt Nunes about network time series, but he can tell you about that. And just to finish, a summary slide. I thought I'd give you one last time series, and this was a search on Web of Knowledge, I think, and it's the number of papers each year with the words locally stationary time series either in the title or the abstract. Now I know you've seen this kind of thing millions of times, some cheesy picture of we're on an upward curve, but we are. Look where we are now. Look at this last year, 2013, all these papers, right? Now what it meant was when we first started looking at this, we had to read like 3 or 4 papers a year, and then you'd be like an expert in the field. I mean, look how much work you have to do now, right? Over 2 years, 50 papers or something, right? So and doubling, and it just shows how much more money we need from the funding agencies to get people to read all these papers. But in summary, this is really all I wanted to say was non-stationary time series. It's a great field to work in. There's a multitude of things you can do. We should pay attention to the multitude of basis functions. There's lots of different things that we can do, and forecastings are fantastic too. All right, thank you for listening.
Guy, thanks. That was a great talk. I really enjoyed that. Since presumably there's lots of different ways in which you could choose this basis. I mean, there's no preferred basis, right? So, could you comment on ways to go about choosing the basis? I mean, I know in signal processing people get assessed by things like sparsity, but I mean, I don't. I'm not.
I think there are ways of choosing the basis, and a lot of the work that people like Reiner did with the Whittle likelihood for locally stationary, and that's basically a way of fitting a model to a kind of, for the time varying AR, you get the parameters out of that. So you could probably do something like that for here. So you have the Whittle likelihood, you have these different models, and see what it gives you in terms of the fit. But I suspect you're going to get a lot of wildly different models fitting the series well. I mean, look what happens in ordinary stationary time series, and ask the question, fit an ARMA model and get some piece of automatic software to give you the top 5 models or something. It'll do that quite happily, and the likelihoods will be a bit different, but not that different. So it's going to be, one of the reasons I've steered away from that is because I think it's really a very hard problem, whereas the test of stationarity is a bit more immediate. I mean, I'm sure there's people in the audience that know more than me how to do that. So I don't think it's hopeless, but I think it's going to be really challenging.
Just a comment to your question. I guess your question was a little bit more in direction. So I have many basis representations, multitude of, Cramér-like or whatever approximation to what should I try in the first place. It's complementary to what you said, Guy. I would advertise to use, if possible, some a priori information. I'm not a Bayesian at all, but I think if your problem is such that you're after like segmentation with abrupt changes and having quite of reliable information between the breaks, then you should do something completely different as if you think, okay, I'm interested in having a robust overall, evolution could be slower or faster, it doesn't really matter. So I think in the first place you should take a minute or two to think about what you are after. And then try, if you get a feeling for that, to use the least complex method in order to achieve this goal. And then you get into these fine-tunings, right? But that might be something, and then there is, for some of the methods, people came up with some compromise between complexity and flexibility. So for example, if you get into a specific library, say, I don't know, of local cosine functions, and you want to fit the best one, then there is this technology of best basis search, with matching pursuit or whatever signal processing like methods. But statisticians have contributed to understanding what's going on there. So what kind of penalization to use to protect against overfitting and stuff like that. So in a sense, I think it should be like a mix of use your own intelligent pre-processing to narrow down, and then try to apply what statisticians have pinned down for specific situations and specific methods. That would be a little bit what I would
Of course, I should have said Flex as well on there.
Yeah.
Yeah, just a quick comment. I think it's always important to discuss stationarity and non-stationarity in conjunction with the problem we're trying to solve. For example, Philip Preuss and myself have recently been working on a nice little project where we show that sometimes it's better to choose a stationary model even if we know that the system is non-stationary, and vice versa. And that's when we have a specific task in mind, for example, forecasting, etc. And this also relates to the first question about how to choose the approach, not just the basis, but also stationarity versus non-stationarity.
Absolutely.
Yeah, I think this may be related to the last comment. I'm always interested in the interpretation of results which might be obtained by such methods, and perhaps also implications for action. Looking at your wind data from Bodmin Moor, you have a nice steady regime which apparently suddenly changes. You apply a test, you get a p-value so tiny that it could burrow into anything, and the conclusion is that that process is not stationary, and that event is put down to the arrival of a weather system which interrupts the preceding process and cannot be attributed to the process generating the preceding data. However, this now moves us up a level, because the arrival of such interrupting weather systems may itself be attributable to a stationary process. Every so often you get hit by a weather system, and it's like a Poisson process or something. And then the process governing the arrival of the weather systems may itself taking up another level. You can have a kind of hierarchy of these things, which at any one level will be stationary, but such that it generates apparent non-stationarity at lower levels. And there may be one level that you're comfortable with for present purposes, whatever those purposes may be. So depending on what you want to do with the result, you will settle on, well, it's been nice steady weather for 2 weeks, but don't count on it for the next week, short term. Is the climate changing? Look at it over a year or 10 years, longer term, etc. And in the limit, you can imagine yourself in a kind of a universe populated by millions of totally different stationary models, with the world doing a kind of random tour, stopping for a while on this beach, in that hotel, on that mountaintop, whatever, subject to overall what would, in the global view, be stationary, but viewed locally would not be stationary. So this, I think, ties in with what you mentioned earlier on, the mixture, composition of compound processes. Just a comment.
Okay, well, thank you. Of course, what I showed was a very silly, trivial toy example. The real professionals use absolutely every ounce of idea that they can, directional, other data, and some of the things that you're mentioning. If there's a way to squeeze more money out of the thing, they'll do it.
Oh yes, indeed. But there comes a point where you decide to stop and say that you're comfortable with what you've done. And in any case, you never really have enough data to identify everything which is going on. So you have to allow the existence of this sort of super world populated by unimaginable nasties, so to speak, which one birthday you might encounter. So there's a level at which you decide that this model is good enough, either good enough to give you a working understanding, or good enough as a basis for action, or possibly to stimulate, we can't fit any known model to this, let's think about it, type of action.
Okay, thank you.
So Guy, I know you spent a lot of time looking at tests of stationarity in the last year or two, and I noted your comments about the area really taking off now in the last couple of years as well, and the number of outputs coming in. So where's it going to go? What problems are to be thought about and resolved there, do you think?
Well, I mean, I think I had I like the branching out slide. I think there's a lot of interesting problems. I mean, I noticed in the 90, was it 18? No, the 89 book by Robinson, and I forget, Granando was the other editor maybe. You had a paper in there, I think. And there's a nice paper in there by Subba Rao and Richard Chandler about point processes and the spectral representation. And you know, again, it's probably my ignorance. I'll go back and probably find 6 papers from there, but I think that's a whole area that could explode on its own, given the usefulness of that kind of data. So that branching out slide was the one really I'd point you to. Dave?
With regard to the test of stationarity, what I found interesting was that there's a diagnostic for what is the origin of the non-stationarity built into them.
Yeah.
But you also said that these representations are not unique, so my question would be, if you use 2 different representations, would they give you not just the same small p-value, but would they give you the same diagnostics?
Well, I haven't got any theory on that. That's a very interesting question, though from empirical observation there's a large degree of consistency, but you're right, sometimes they do poke up in different areas. It's an interesting, you could do some theory on that, I guess.
Is there an estimate of variability in these 2-headed arrows?
Yeah, you
You
could
can tell
yeah,
how much longer it might have been.
Yeah, I've not done that, but that's something you could be looked at. Yeah. Thank you.
Okay, so I think we'll leave it there for today. There is now a wine reception and sort of posters, and then talks start again tomorrow at 9:30. But if we could just finish by thanking Guy again and all these people.